we're going to use Newton-Raphson, Newton's method. And you probably did this in your undergraduate, your first course in computer programming. I mean, if you didn't learn anything else in that class, you probably learned how to do Newton's method, right? So, of course, here we have a system of equations. So we're going to define a residual that is K U U minus F equal to 0. And of course, it's not actually going to be equal to 0. The residual is not. There's going to be some non-zero, but the equation on the right should be 0. But depending on what our u is, if it's not exact, it won't be 0. Right? There'll be some residual. And so what we want to do is drive that residual to 0. And so if we Taylor expand the residual about n plus 1 equal to n, all these u's are vectors. In fact, the residual is a vector too. So just rewriting that equation, remember, we're going to try to drive the residual to 0. So, and then we're just going to define the partial of r with respect to u as the tangent stiffness. Okay, evaluate it at step n, and then you have that delta u there. So, yeah. So this is the tangent stiffness matrix. Evaluated at u equal to un. Right? So then with that, we can update the displacements. Like that. Or if we write out what r is, and then we can update the displacements u equals un plus delta u, which we solve for. So if we go back now to the same problem, and use Newton's method, so same initial guess I had before when I tried to use Gauss-Seidel. I use Newton's method. Hones it right in on the root. And Newton's method has we talked a little bit about it last time. It has a quadratic convergence property. So in other words, that residual will be cut in half every step you take. Likewise for the other case. So it works, the point is here, it works for both initial conditions. So it'll find both roots. So remember, from a mechanistic point of view, when we solve finite elements, especially when the easiest way to think about it, even though the same can be true for a fluid or something, but if you remember, when we're going back to like the Ritz method and other things, we can write a potential energy functional, and the stationary value of that potential energy functional is the conservation of momentum equation, right? The same holds in the discrete case, right? If you substituted in your approximates into your potential energy functional, the minimization of that is the finite element model, essentially, and the solution to that gives a global energy minima. Okay. In general, not necessarily a minima, right? A stationary value, a minimum, a maximum, or a saddle point. In the case of elasticity, it is a minima, right? It's a minimum. So the point is, in that case, there's not two roots. There's one global minima that you'll converge to. And so the primary application of these nonlinear solvers for us